All right, so we're warming up. On the back of worksheet 13, we have a regression equation that I want you guys to look at. And I already warned the class, but when you're looking at the answer key, I stole that answer from the book, and the book is like, you know, superstar, rockstar, gives answers in perfect radian mode form. I don't expect that from you. I expect decimal answers on these. So on your bookwork, numbers 20 and 22, you probably shouldn't match the key. That would be weird and suspicious. Okay? So let's get this data entered into list 1 and list 2. Oh, this is not... Okay, this is weird. So we're looping through... We're starting in August. All right, what is this even about? Oh, the cost of natural gas. Okay, so we're going to start... You can technically choose to start your data wherever you want. I'm going to pretend August is 1. So what I'm going to do is over the month word, I'm just going to write 1, 2, 3, 4, and so on. And then... It's not like your traditional calendar year. That's what we're doing here. So we learned from, what day did I see you last? Thursday? We learned from Thursday's worksheet that you can technically start a sine or cosine function, like really wherever you want. Or we call those sinusoidal graphs, depending on, well, not depending on anything. They're all sinusoidal. So change these all to the appropriate numbers, blah, blah, blah. Continue on. This goes out to 12. And then start typing in your data. I'm going to pause my video and check my data because I don't know if I did it right. So I think I have my data entered properly. A few lessons that we learned from our excursion and regression last week. What mode should your calculator be in right now? For these questions, they have to be in radian mode. So let's go check that. I am in radian mode. Good deal. The next thing you might want to do is take a look at the scatter plot. So make sure nothing is in y equals. We don't want to graph anything else right now. And then I would just zoom stat this and see what it shows you. Oh, I didn't turn my plot on. Okay. Turn the plot on and then zoom stat. All right, there we go. So definitely sinusoidal. The fact is, you know, whether you call it a sine or cosine doesn't matter. Your calculator thinking was going to defer this to a sine. Jetta. So, we're going to want to do sinusoidal regression in our regression menu. So stat, over to calc, and then towards the bottom of the list you'll see sine reg, sinusoidal regression. And we're just going to leave the iterations at 3. It just defaults to that. On my older calculators it doesn't ask you for anything, so don't worry about, just leave it as default. I always put my data in list 1 and list 2 for these because I usually don't have more than one set of data in anyways. Make sure the period is blank so it doesn't try to adjust the period. It just gives you the natural formula. Please do store this because we're going to move on and actually ask you to use the equation in a minute. And I do not want to type this out. And calculate. So from this screen, you do want to steal this data and write it on your paper. So y equals 46.8 sine. And then remember this version is the unfactored version of the sine graph. So the phase shift and the b are all multiplied together here. You can't see the natural phase shift without factoring out the b. By the way, the b is 0.52-ish. And then when we jot that down on the paper, that's going to be one part of your answer for your test, which, by the way, is currently scheduled for Friday. So we'll see. And then they want, oh, they don't want anything. Why do I keep thinking they want me to do things in this question? All right, let's pretend. Okay, so there's a homework question that says, using your model, tell me I think the question in your homework is about like temperature in the different months of the calendar year. So on this question, let's say according to the model, what is the average cost of natural gas in December? So I know according to my chart, December, which is month 5, is supposed to cost $92.70. But I think if you actually use your model, you're not going to get exactly that answer because we know the model's not perfect. For instance, hit graph. I think it's pretty good. But hit trace. And then get up on the curve instead of the scatter plot and type x equals 5. So it's really not far off. It says 92.2. And according to the raw data, it was 92.7. So pretty good. Not exact, but pretty good. All right. The next questions that are on the review section here. Oh, these are good ones, because this does show up on your next test, remember. The angular and linear velocity stuff is going to show up again. Speaking of that, we're going to do some questions here, but a few of you really missed the target on section 4.3, which is where you were supposed to use the unit circle and give me the trig ratios for, like, you know, what's the sign at 5 pi over 6 kind of questions. So if you got a lot of things wrong in that section, you know, you might want to investigate some tutoring time with me, or just rewatching that part of the lesson, or just practicing those questions again. At the very least, make corrections to your test. Most of you, when you had issues on that section, a lot of kids had issues with 0 versus undefined. What happens when you take the reciprocal of a 0? And then a few of you had issues with reference angles, I believe, in that middle section where it was multiple choice. So all that shows up again on the test. It's going to look a little smaller this time, but the main ideas are all going to be there. So make sure you can hit all 3 of those concepts that are on that section. But to section 4.2. How many radians per second must the pulley turn in order to start? So they went ahead and said find the angular velocity, but remember our angular velocity is always measured in radians per second, and the clue they gave you is 150 revolutions per minute. So there's actually 2 things I need you to convert. You start with what you have. Whoa. Try again. You start with what you have, which is 150 rotations or revolutions per minute. I used the wrong word. They said revolutions. Does not matter, though. And then we're going to convert revolutions to radians, and then they also want per second, so we have to convert minutes to seconds. So I'm going to go 2 pi radians per 1 revolution. That'll convert the radians, 2 radians. And then in 1 minute, that's equivalent to 60 seconds. So my favorite part of these questions is to make sure my labels work out. I'm going to end up with radians per second. So I love a decimal answer for this question. I do not appreciate these done in terms of pi, but it's up to you. I don't really care. I'll put both answers on my answer key. Why? Because they're like real life questions and no one runs around going like 60 pi, you know. So I know. But I keep it in my calculator for the next step, so I don't really care. Like, I just use the answer. But a valid point. I just, like, you know, in terms of answering these, like, I just think it's really weird to be, like, shouting out pi answers. But whatever. So what'd you get? So Jenna's going to give me 5 pi, and the rest of the humans are going to give me that thing, yeah. So 5 pi radians per second, totally good answer, or 15.7 radians per second. And then they do want you to convert now to linear velocity, which my favorite formula for that is angular velocity times the radius. So where's the clue? Oh, that's nice. It's already in feet. So there's radius. We already have angular velocity. I'll use Jenna's trick and just use 5 pi. The radius is 0.24. If you guys are typing like by hand 15.7, you're going to have a little different answer. She's right about truncation. If you kept the decimal in your calculator and just say times 0.24, you're going to be fine. Your answer should come out to 1.2 pi feet per second, or the humanoid answer would be 3.8 feet per second, I think. And I'll have both of these on my answer key as far as testing. Now here's the trouble that some of us run into. A few of us tried to give pi answers, in terms of pi answers, and then didn't put the pi down. Like they'd say 1.2. And I go, like I know what you did. And that makes sense to like a human, an answer of a decimal, but like if you left yours in terms of pi, pi is still there, so be careful. All right, ignore that. You already did that for homework this weekend, right, kids? Yes, Mrs. Abruzzo. I love your homework. It's very fulfilling and makes me feel like I'm going to ace my test. Seriously, who did their homework? Some. Thank you. Thank you. Liar. Well, it's all right. You just got lots of homework tonight then. That's all. So today we're going to do modeling. It's going to be a hoot. You ready? It actually transfers nicely from our lesson on Thursday. Today's Tuesday. Yeah. Okay. So We're going to refer to these as sinusoidal functions, but we learned on Thursday that me calling it a sinusoidal function does not mean that you are married to using the sine function. You could use the cosine function. It's all a matter of, like, where's the easiest place for me to start. So, unfortunately, you guys can give me a variety of different answers when it comes to creating a model, but if I ever ask you to use your model to predict, in that case, we should all be getting the same answer because your models are going to all develop the same answers, assuming we're all right. So the motto for today is do what's easiest. So if making this start somewhere else on the paper makes your life easier, do that. Okay, you know me, I'm lazy. I'm not going to do this the difficult way. So the sketching of the curve, I think, is probably the most important part, even though we're not going to make them look really pretty, but we are going to do some labeling. So Rashad is riding a Ferris wheel, and his distance from the ground varies sinusoidally, which just means it has this weird wave shape. So when the last seat is filled and the Ferris wheel starts, Rashad's seat is at a position random, like over here. Turns out, I actually don't care about that. I'm not going to start our function where Rashad is right now. I'm going to be clever. Keep reading. Let t be the number of seconds. So this is where you got to read really carefully, guys. They're defining the variables for you. You must use t instead of x or theta in this problem. Blah, blah, blah. Rashad determines that it takes him 3 seconds to reach the top, which is 43 feet above the ground. Okay, so right there, I'm going to ignore the 3-second thing for a moment, and I would like you to think about this max line up here. When he's at the top of the Ferris wheel, he's 43 feet above the ground. Of course, we're going to call 0 the ground. There's a really important clue snuck in here. It says he determines that he's back at his original position after 8 seconds. What is that fancy talk for? How long it takes for him to complete 1 full revolution, also known as? That's period. Yeah. I know there's a clue over there about, like, frequency. It says revolute. Oh, well, that is period. Ignore my frequency comment. We'll come back to frequency in a moment. Sorry. Okay, so this clue here that I kind of accidentally crossed off, it takes him 3 seconds to reach the top. Wouldn't it be super easy if we just pretend our curve starts there? Because if that's the start of my curve, then I could pretend I'm a cosine function. Okay. All right, let's talk about that 40-foot diameter business. If this diameter of the wheel is 40 feet, can you tell me how high off the ground the bottom of the wheel is then? It's got to be 3 feet off the ground, right? So if the diameter is 40 feet, that would be the entire range of your function. It's going to go anywhere from 3 feet at a low point and then all the way up to 43 feet. Because obviously your Ferris wheels are not going to drag on the ground. This clue about diameter being 40 feet, that is the range. But that's not part of our function, right? We don't actually ask you for the range ever. We ask you for amplitude and for midline. So let's go ahead and either visualize or calculate both of those things. Anyone figure out where this midline is? It is at 26. And, no, 23 is what you said. You're fine, you're fine. I've been very sick all weekend, and I think my entire ear canal on both sides are closed. So you're going to have to yell at me. Okay, 23, you could either calculate it or you could visualize it. But for me, apparently I'm going to have to calculate today because I can't visualize anything. Remember how the entire range was 40, which means halfway, the amplitude would be 20. So 20 from here to here and 20 from here to here. There we go. Speaking of 20, we can throw that into our formula. Okay, now guys, let's talk about this. If I'm pretending that my cosine function, oops, I spoiled it. If my function starts right here, what type of a function do we have? Cosine. And since it's starting at the top, the a value is not negative, so I'm going to go ahead and just throw in that the a value, the amplitude is 20. Cosine. Okay, now, leave yourself a pretty big parenthesis set for a moment. Since I'm choosing to start my function right here, we have to accept that we have a phase shift. What time was it when we reached the top? 3 seconds, yeah, to get from where he was to the top. So he's got a phase shift of right 3 units. We're going to incorporate that into our calculations in a moment. but we need to calculate something else first. I'm going to go ahead and write t minus 3. There's one more easy thing we can fill in here. The midline, we decided was at 23, so plus 23. What's the last thing I got to calculate is b. So in order to calculate b, you can just take your formula for finding period that you have memorized and flip it around if you'd like, or you could memorize an additional formula that says b is 2 pi divided by the period. So 2 pi divided by the period, what was the period again? 8. So b comes out to, please do reduce this though, pi over 4. In these real life questions, you're going to get a lot of b values that have pi's in them because your period is not going to be measured in terms of pi, generally speaking. It's going to be measured in time, like 8 seconds. So there's our formula. Anyone have any problems? And I went ahead and set it up in what we call factored form because there's really no point in me distributing the pi over 4 into anything. It's just going to get grosser if I do that. Now, if you went a little rogue on me and you were like, no, Abruzzo, I'd like to start this at 0. You have a lot more work to do. So I don't know why you'd want to do that. So let's just use this function, okay? Using your calculator, okay, that means grab your calculator. Go to y equals, and it does say, what mode are you in? Well, we should be in radian because we just did that question, right? So make sure you're in radian mode. I'm going to pause while I get everything entered. All right, so we've carefully typed our function into y1. You don't have to do any simplifying, of course. And then it asks about window. So our window is just from our last question. It's, it might be different than mine, but that's fine because we haven't adjusted it yet. So x represents t in your problem, which is time that you're on the Ferris wheel. So what would be an appropriate place to start Rashad's time on the Ferris wheel? 0 would make sense. I don't really care what happened before he got on the Ferris wheel. And I don't really know much about his Ferris wheel here, but they want me eventually to predict his height at like 6 seconds, 4 1/3 seconds, 9 seconds, and 0 seconds. So I just got to make sure whatever time I end my window, it at least encompasses all those. So I'm going to go to like 12 seconds for no particular reason. Now, with this being in radian mode, some people argue, oh, well, I should do something like, I should go out to like 3 pi or something. I don't really care because I'm just going to use decimal answers here, so I don't care if the window fits like radian numbers nicely right now. The y's, I think we already have a really good, I don't have a good window, but on our paper we have a good window for where our y's should look. I know it technically goes from 3 to 43, but I always like to extend the window a little beyond that. So I'm going to go 0 to 45. So that's the benefit to kind of sketching out a really awful graph before you get going on the calculators. You know what you should be seeing. And let's try. Let's see what happens. It's beautiful. Look at that. So then the question says, tell me Rashad's height at 6 seconds. So easiest way to do that now is to pull up your cursor by hitting trace. Oh, look at that. Did that happen for you too? Oh, magical. Well, that's because it's the middle of the window, Abruzzo, you idiot. All right, so 6 seconds. Jot down Rashad's height. This is fascinating stuff. I want to meet this Rashad who needs to know where he is on the Ferris wheel at any given time. He sounds like a good candidate for our math team, doesn't he? Let's recruit him. All right, and then 4 1/3 seconds. Now, I know some people are like, I'm going to write 4.3 and call it good enough. Technically, you should be writing 4 1/3 like this. I don't know if my calculator likes that, but yeah, it did. That is a very specific number, and it gave you a very specific height of 33. And then at 9, 23, and then at 0. So mystery solved, guys. Remember a while ago where we were like, we didn't really know how high up off the ground Rashad was when he started his Ferris wheel problem? Well, now we know. So if you were just horribly curious about that, now you know. So if you'd like to rewrite your function so that it is not phase shifted, you have more information now where you could figure that out. Or not. Let's move on to the next question. So you can imagine how fun these are going to be for your teacher to grade, right? Oh, I don't have Adobe Flash. Apparently that was an animation of a Ferris wheel. Sorry. Oh, Flower, you're so cute with your animations. All right, physics. Do you guys do this stuff in physics anymore? I don't even know what happens in physics these days. We used to do this problem a lot where you'd attach a weight to like a spring. And then it would model, depending on the strength of the spring, it would model a different wave sinusoidally with time. This one, let's see. The distance from the floor varies sinusoidally. You can, okay, you start the stopwatch. When the watch reads 0.3 seconds, the weight reaches a high point of 60 centimeters. Okay, so this one's kind of, they've already labeled some things for me, which is nice. I can use all the help I can get. But the high point is 60 centimeters. So that's one of the things I'm going to mark here. I'm going to call this the maximum line, which is at 60 centimeters. But I'm going to leave labels off for now. And then if I continue reading, there's a low point at 40. So your little weight is going to toggle between those two heights. So the other thing that I kind of read over there quickly was that when the watch reads 0.3 seconds, that's when it reaches its high point. So I think it's kind of like that Ferris wheel problem where I'm going to choose to start my wave right there. So at 0.3 seconds is where I'm going to start, but it's at the high point up here. So this is 0.3, 60. And then at 1.8 seconds, 6, 7, 8, right here, it reaches a low point of 40. Well, that's curious. So there's like a whole nother part of this curve that we're not even going to be able to draw in, but that's okay. All right, let's start with the obvious stuff. Where's the middle? 50. Now that's either through inspection or through calculation. You can use that midline formula where you add them up and divide by 2. But yes, the midline is at 50, so I'm going to kind of cheat and just put a plus 50 over here. The amplitude, the size of your wave from midline to top or midline to bottom would be 10. And since we're choosing to start our function at the top, we're going to have a positive cosine A value. So 10. I spilled the beans again. It's cosine. All right, let's talk about this. We know we're going to have to calculate something for B. And since we're choosing to start our cosine curve shifted over to the right, we do have a phase shift. Now, read carefully. What do they want me to use for, instead of x, they want t. So you're going to say t shifted to the right, 0.3, so minus 0.3. Close that parenthesis, and then there's a secondary parenthesis that's closed. So now it's just a matter of calculating B. We don't actually have a full cycle, so you guys don't have the period. What you have is half of the period. So how long does it take, let's just start with this first question, for your spring to go through half of its cycle? Well, it was from 0.3, remember, to 1.8. How long was that? That's 1.5 seconds. So if you continued on and got, I can't draw it because I ran out of room, but if you continued on and got to the end of the cycle, how long was that? It's 3. So knowing that the period is 3 seconds, now I can calculate B. It's 2 pi divided by period. So 2 pi divided by 3. And that doesn't simplify, so just throw it right into the formula. And if I had my life to live over again, I would have written a lot clearer, but I didn't. All right, so there's a very ugly function. And you don't need to simplify it in any way, because anything from here on out, we're probably just going to use our graphing calculator. Or in this case, well, there are 2 questions. So sure, why not? Go ahead and get this entered into Y1. So after carefully typing in our cosine function, remember our window from the last question is from that Ferris wheel question. I don't think that window's appropriate anymore, guys. So this spring is, they're going to ask me questions about 17.2 seconds in a moment. So we need to make sure that if we're going to use our graph, that our graph goes out that far at least. So I'm going to go to 18 seconds. And then I can clearly see a good range. You can go 40 to 60 if you want, but I always like to give a little leeway there. So I'm going to go 35 to 65. Crazy like that. Oh, it didn't like something. What did I do? Oh, that's bad. Try again. Okay. Hypnotic, isn't it? It's fascinating. Okay, so this question says, at 17.2 seconds, what you got? I don't know, let's figure it out. Trace, 17.2. You could have found this out by either, you could have just manually plugged in a 17.2 as well, or gone to your table. So I got 43.3 centimeters. Make sure you're labeling these answers. And then what is the distance from the floor when you first started the stopwatch? Well, your time when you first start the stopwatch would be time of 0. So again, if you wanted to go back in time and figure out a different function for this, you sure could, but my answer to that is y. I don't know a good answer to that. Don't do it. All right, 58.1 centimeters. All right, so far so good. So I don't mind trig modeling as a learner or a student, because there's really not much you can do wrong as far as like where you want to start, but you sure can make your life worse if you aren't choosing carefully. Oh, a nice tsunami. Uplifting moment for us. Good talks. There's not a lot of good sine and cosine application questions. It's a lot of Ferris wheels and tsunamis in your future, okay? Fast-moving ocean wave, yeah. Okay, underwater earthquake. The water first goes down to its normal level, and then it rises an equal distance above the sea level, is what they mean, and then returns. Good to know. You ever seen those underwater pictures of just general waves? Like, forget tsunamis, because those are scary, but like a wave, they're kind of awesome. I don't want to be in one, but it's cool. So the period is 15 minutes. Well, that's a very nice clue to give us. Thank you. And then it says, suppose the tsunami, oh my gosh, this is like your birthday. Just giving you stuff. The amplitude is 10 meters as it approaches the pier at Honolulu. And the normal depth of the water is 9 meters. My goodness, they just flat out gave you like almost everything you needed. When they say the normal depth, that's like the normal sea level they're referring to. So this right here, this is your midline. And obviously amplitude means that's the A value. Now we might have to play with the sign of A, but the size of A is 10. The period is 15, which is going to help us calculate B. So the first thing I want you to do is kind of sketch it out. And I know some of you, many of you, all of you, are smart enough to create this without a picture, but man, as your grader, let me tell you, the picture really helps. Because if you forget to change the sign of A when necessary, I can revert back to your picture and show you like, oh, see it's reflected. So let's see here. The graph. Midline at 9. Sure. Amplitude of 10. So this max line up here is going to be at 19 feet. And then remember amplitude of 10. So we're going to call this -1, but it just means like 1 foot below sea level. Okay. So the tsunami wave, what does it say? I feel like I missed an important clue somewhere. Oh, yep. It says right here. The water first goes down from its normal level. So let's pretend that the water starts at the normal level at time of, you can call it time of 0, it doesn't really matter because they already gave us the period. And then if your graph is going to move down first, hello, and then come back, you're going to get something like this. Now that was a really important clue. If we're going to call this graph a sine graph that starts at time of 0, because what do we have to incorporate now into our function? Since it's moving downwards first, that means we have a reflection. So, real quick, I'm going to throw a negative in front of this because I'm going to forget. And then the amplitude, they already flat out told you it was a 10, so -10. What shape are we referring to if we're going to pretend this is the start of our wave, which we should? It's called sine. Now because it's going to start at time of 0, we can incorporate no phase shift into this one. So, the only thing we're going to need to do, oh, and our midline was 9. The only thing we're going to need to do is find the B value, and they flat out told you the period. So B value is 2 pi divided by the period, Okay, that doesn't even reduce. Good to know. So now we're going to answer some questions, which means we're going to go back to our calculator. That seems like the good way to go on these questions. All right, so this time we're carefully typing. Because you don't have that phase shift anymore, there shouldn't be a double parenthesis closing, so just that single set of parentheses. And then I'm going to investigate the questions a little bit. They want to know the depth at 2 minutes, 4 minutes, and 12 minutes. So I'm actually just going to leave my x's as they were. But for the y's, let's change those up. Let's see. I'm going to go like -2 to 20. And let's see. Well, that's beautiful. Okay, so answering some questions at 2 minutes. Trace 2. Sea level, or the water level is at 1.6 meters. Make sure you're labeling these questions. At 4 minutes, we got -0.9 meters. And then at 12 minutes, we got 18.5 meters. And then it does say, according to your model, what will the minimum depth of the water be? And we already knew that minimum to be -1 meters. But this last part is, how do you interpret that for the real world? Because that's a little confusing. So -1, we talked about like being according to sea level. Like when they measure the depth of your water, it's always to sea level. So this swell of the wave is going like 1 meter below sea level is the interpretation of that. So, got to get water from somewhere, right? That's what they do. And then the wavelength of a wave is the distance from the crest of the wave, that the distance a crest of a wave travels in one period. So it is also equal to the distance between two adjacent crests. Okay. If a tsunami travels 1,200 kilometers per hour, what is the wavelength? How long did it take? Well, what was the period? 15 minutes, right? We need to convert this to the hours to minutes or vice versa. So whatever you guys want to do. I'm going to take the... Does it say how they want it answered? No. I'm going to take the period and just call it, instead of 15 minutes, can we call it 0.25 of an hour? Okay. So take the 1,200 kilometers per hour and multiply it by 0.25 of an hour. What'd you get? Is it 3,000 kilometers? Okay. No? 300? No. 300 kilometers? Okay. Like I said. Did I do something stupid? What am I doing? What? 3,000 of a quarter. Yeah, that does make sense. It's 3,000? 1,200 times 0.25 is 3... No. Oh, that's because I wrote 1,200. Is it 12,000? 1,200. 1,200. It's 300. 300. I don't know what I'm doing, guys. I don't know. 300, yeah. Did you do what I did and type 12,000? Oh, that too. Decimals, they're a thing, and they kill people, so be careful. All right. 300. Sorry. I don't know, when you give me that skeptical look, I just doubt everything I've done all morning. I just go, something's wrong. Something horrible has happened. Okay, so the wavelength is 300 feet. Good to know. I don't know. I don't really know anything about tsunamis, guys. I'm going to have to investigate that a little bit more. This last question about the rocket, we're going to stop for today, but I'm going to come back and do this one tomorrow. However, you guys can most definitely get a head start on, no, I don't think this is the right assignment, so hold on. You can get a head start on what will be your last homework assignment in this homework check. You're doing 1, 2, 3, 4. You're not doing 6. You're doing 7. We scribbled out 8, and you're doing 10. So we have shortened this to the shortest assignment we could possibly give you, okay? So it's on the next 2 worksheets. It's like a two-parter. This homework check, remember, is going to be due when we take our summative, which right now is scheduled for Friday. So I'm going to tell you this. I'm going to give you question opportunities in class over the next couple days. And if people don't ask me questions, then I'm just going to move on and teach the next lesson that's on the next test. So show up with questions and make them good.